Hi, Assalamualaikum. Today I will be presenting the company profile and executive board of our company, Tempro TM, which perfectly combines biotechnology with commercial viability. As a biotechnology-based food enterprise, our core focus is specializing in premium fermented soybean products. Our competitive advantage lies in producing safe, highly nutritious, and plant-based protein through controlled fermentation technology that is strictly compliant with GMP and HACCP standards. Driven by our vision to become a leading producer of innovative fermented food in Southeast Asia, our mission is to deliver sustainable, safe, and premium quality bioproducts to the market. This execution is led by our specialized executive board consisting of Karina Sakira binti Zali as project manager, Nur Afika binti Ramli as plant design and GMP officer, Nazira Aima binti Fauzi as production manager, Dania Kristina Balkis binti Azman as risk assessment and QA officer, and Husna Shakira binti Zahar as product development and marketing officers. Together, this structured team guarantees absolute operational efficiency and safety from processing to distribution. Thank you. Moving forward, our project focuses on how controlled fermentation addresses the demand for sustainable functional foods through three main pillars. First, under tradition meets biotypes. We upgrade traditional tempeh production using strictly controlled environments to prevent contamination. Second, for market dynamics, we meet the rising global demand for healthy, plant-based protein rich in fiber, vitamins, and minerals. Third, through engineering quality, we apply advanced fermentation technology to ensure product consistency, fulfill GMP requirements, and uphold industrial food safety. Finally, our progress is guided by our project roadmap, which systematically moves from literature review, plan design, and process development into GMP planning, risk assessment, and product development before concluding with our final report and presentation. Thank you.
Tempeh is produced through solid-state fermentation using the fungus Rhizophus oligospores. During fermentation, the fungus produces enzymes that break down complex nutrients into simpler compounds, making tempeh easier to digest and increasing its nutritional value. Our company aims to expand the availability of tempeh in Kelantan, where it is currently less accessible. By improving production and distribution, we hope to promote tempeh as affordable, nutritious, and sustainable food source. The production process consists of two main stages, including upstream and downstream process. In the upstream stage, soybeans are received, washed, soaked, dehulled, boiled, and cooled to prepare a suitable substrate for fungal growth. Next, in the downstream stage, the soybeans are inoculated with Rhizophus oligospores, fermented under controlled conditions, cut, packaged, stored under refrigeration, and distributed to consumer. Key equipment used include soaking tanks, dehulling machine, steam cookers, cooling trays, incubation room with temperature controllers, packaging machine cool, storage units, and delivery vehicles.
This slide shows how our product Tempro translates bioprocess engineering into market value. First, the nutritional density of Tempro is achieved through a controlled fermentation process using Rhizophus oligosporus. This controlled environment ensures consistent product quality, enhance nutritional value, and food safety. Second, the product is packaged using an eco-friendly vacuum seal. This packaging helps maintain the biological integrity and freshness of the tempeh, while also extending its shelf life and protecting product quality during storage and transportation. Another important feature is the QR traceability code. Consumer can scan the QR code to access HACCP badge documentation and supply chain information. This improves transparency, traceability, and consumer confidence in the product. In terms of product architecture, Tempro is available in several variations, including original, organic, frozen, cube, and chips. This option allows the product to meet different consumer preferences and market demands. Finally, Our target market include health-conscious consumer, vegetarians, athletes, and functional food consumer who are looking for nutrients, sustainable, and protein-rich food alternative. Overall, Tempro demonstrate how bioprocess engineering can be transformed into a high-value commercial product that combine nutrition, quality assurance, sustainability, and market adaptability.
Next, I will explain how the BSL-1 facility architecture physically enforces GMP hygiene standards. Although tempeh production uses Rhizopus oligosporus, which is classified as a biosafety level 1 microorganism, proper facility design is still essential to maintain food safety and product quality. As shown in the facility layout, the plant is divided into different hygiene zones based on contamination risk. The non-production area include the reception, office, meeting room, and changing room. These areas require only basic hygiene practices because they do not involve direct food processing. The low-risk area is where washroom and cold storage take place. Since the soybeans are still considered as a raw material, standard hygiene controls are still applied. The medium risk area includes soaking, boiling, dehuiling, cutting, labeling, packaging, and distribution. At this stage, additional hygiene measures are necessary to prevent contamination after processing. The high risk area consists of inoculation, fermentation, and cooling. This operation involves direct contact with the product and therefore requires stricter hygiene controls, restricted access, and proper use of personal protective equipment. By physically separating this area, the facility minimizes cross-contamination between different production stages. These zoning strategies support GMP compliance, improve process control, and ensure the production of safe and high-quality tempeh products.
This slide shows the critical control points, or CCP, this was identified in our tempeh production plan layout. These are the most critical stages where control measures must be applied to prevent contamination and ensure product safety. The first CCP is the washroom and sanitation area. All personnel must pass through this point before entering the production zone. Proper hand washing and sanitation help prevent microorganisms from being introduced into the processing area. The second CCP is the inoculation and fermentation process. This is the most biologically sensitive stage because the fungal culture is actively growing. Any contamination from workers, equipment, or air can interfere with fermentation and affect the quality and safety of the tempeh. The third CCP is the packaging stage. This is the final control point where the finished product is sealed and protected from the external environment. Maintaining hygiene during packaging is essential to prevent post-processing contamination. This slide illustrates our defense in-depth strategy, which uses multiple layers of protection to ensure the safety and quality of the commercial byproduct. Instead of relying on a single control measure, several protecting layers work together to reduce contamination risk. The first layer is biological controls. We use only approved and pure starter cultures, specifically Rhizopus oligosporus, and conduct regular environmental monitoring to ensure no unwanted microorganisms are present. Second layer is process control. This includes strict adherence to standard operating procedure, continuous monitoring of temperature and humidity, and proper batch documentation throughout the production. The third layer is personnel control. All personnel are required to wear appropriate PPE, undergo hygiene training, and follow restricted access policies for high-risk production areas. Layer 4 is facility control. The facility is designed with hygiene zoning and a one-way workflow to prevent cross-contamination, while regular preventive maintenance ensure all equipment remains in good condition. At the center of these protective layers is the high-risk biological product, which is continuously safeguarded through HACCP, CCP monitoring, and product traceability system.
Moving on to our facility design, our BSL-1 plan architecture prioritizes safety through strategic core zoning, utilizing a color-coded layout to clearly distinguish between risk levels. The administrative block colored blue house non-production areas including the reception, offices, and changing rooms, while the green code wet processing zone handles tasks like washing, distribution, and cold storage. Thermal and preparation steps such as dehuling, boiling, labeling, and packaging are managed in the yellow section. And the red zone serves as the high-risk biological core dedicated to inoculation and fermentation. To maintain strict process integrity, we have integrated three critical control points into the workflow. First, CCP1 located in the washroom. Second, CCP2 within the inoculation and fermentation core. And the last one is CCP3 at the packaging stage. Finally, the facility design incorporates dedicated supply and return corridors to ensure a controlled, efficient, and safe flow of materials and personnel throughout the plant. Thank you.
Now I'll explain the unidirectional U-shaped process flow. This process flow is designed to ensure that material move in a single direction throughout the production process, from raw material receiving to final product distribution. The process begins with washing, soaking, dehuling, and boiling of soybeans. After boiling, the soybeans are cooled before entering the inoculation and fermentation stage. The fermented product then proceeds to cutting, packaging, labeling, cold storage, and finally distribution. The U-shaped layout was selected because it allows efficient use of production space while maintaining a clear separation between raw materials and finished products. One of the key advantages of this design is that it prevents product backtracking. Raw materials and finished product do not cross paths, which significantly reduces the risk of cross-contamination. In addition, the unidirectional flow improves operational efficiency by creating a logical and continuous production sequence. It also made process monitoring, quality control, and GMP implementation much easier. Overall, the U-shaped process flow enhances food safety, support GMP requirement, and ensure a more efficient and controlled tempeh manufacturing process.
In a bioprocessing facility, controlling material movement is important to ensure byproduct safety and quality. A one-way flow system prevents raw materials from crossing paths with processed or sterilized product. As shown in the layout, the process starts from the receiving area, where materials move through the supply corridor to the processing area. The process continues from soaking, dehulling, boiling, cooling, and inoculation and fermentation. After fermentation, the product moves to packaging, labeling, cold storage, and distribution. The separation of supply and returns corridor helps avoid contamination and improve workflow efficiency. In conclusion, a strict one-way flow system reduces cross-contamination risk and ensures a safe and efficient production process. This slide shows how controlled personnel pathways are used to isolate high-risk biological zones and minimize the risk of contamination within the tempeh production facility. All personnel must follow a designated pathway, starting from the entrance, then moving to the changing room, followed by the washroom for hand sanitization, before entering the production area. This ensures that proper hygiene procedures are completed before staff access any processing zones. The layout also includes a gateway checkpoint at CCP1, which acts as a controlled sanitation barrier. Every worker must pass through this checkpoint before entering production areas, helping to prevent contamination from being carried into the facility. In addition, the facility uses separate supply and return corridors. This separation prevents personnel leaving high-risk areas from crossing paths with workers entering early-stage processing room, reducing the possibility of cross-contamination. By controlling personnel movement and enforcing sanitation produced at critical checkpoints, the facility can effectively protect high-risk biological zones and maintain product safety throughout the production process.
This slide presents the comprehensive risk assessment of Tempro production using a risk matrix. The matrix evaluates hazards based on their likelihood of occurrence and severity of impact. The highest risk hazards are CCP2, microbial or fermentation contamination, and CCP3, packaging failure. These are classified as critical control points because they can directly compromise product safety, quality, and shelf life if not properly controlled. Medium risk hazards include equipment failure during boiling or cooling, chemical cleaning, residues, and human error in sanitation. These hazards require routine monitoring and preventive maintenance to minimize their impact on production. Lower risk hazards include foreign material during receiving or dehuling, as well as storage temperature fluctuation. Although less critical, they are still managed through standard operating procedure. The identified hazards are categorized in biological, physical, chemical, and operational risks. This structured approach allows us to prioritize control measures, focus resources on the most critical risks, and ensure compliance with HACCP and food safety requirements.
Based on our risk assessment, several hazards were identified in tempeh production, including biological, physical, chemical, and operational hazards. To reduce this risk, we implement a 4-pillar risk mitigation strategy. First, facility control, ensure a clean production environment through hygiene zoning, proper material flow, and regular equipment maintenance. This helps prevent biological and physical contamination. Second, process controls involve strict SOP implementation and continuous monitoring of critical parameters such as temperature, humidity, and fermentation time. This control reduces operational risk and ensure consistent product quality. Third, personnel controls focus on employee hygiene, GMP training, and mandatory PPE usage. This minimizes contamination and human error during production. Finally, food safety control include HACCP implementation, monitoring of critical control points, and product traceability. These measures verify that all safety requirements are met before the product reaches consumers.